Hey kids, time to start Unit 5. Area under the curve is how we're going to start this. So as you can see, we are all standing under a curve. So your first homework assignment is from the book, but I want to make sure that you watch this video through, because for some of these book problems, you're going to want to do with a calculator or computer program. And at the end, I'll give you some information on where to find those things. All right, so area under the curve. I want to highlight the fact that we are talking area, right? And for now, that means we are going to be dealing with positive values because area is always positive, right? But we're going to be under some kind of curve. Okay, so I want to remind you about something that you've done you could think of from elementary school. You could think of an axis where your curve isn't quite a curve. Your curve is a rectangle. Let's say I have a constant, quote unquote, curve, right? Let's say this is at a height of 5, and I'm starting here at 0, and I end at 6. The area under this curve is just the area of a rectangle, right? Which is the height of the rectangle times the width of the rectangle. So the area under the curve is 30 square units. Well, if you see Mr. Chase, myself, and Mr. Davis under this curve, if I put an axis system on us, you can see that we don't quite fill up all the area under the curve. If you just take Mr. Chase and myself and Mr. Davis, right, we have some space here that doesn't quite fill in the area between the x-axis and the curve. But when I have a nice constant function, that's not an issue, is it? Okay, so that's kind of like a precursor to or a prequel to what we're going to be doing. So estimating with finite sums. So we are going to be talking about approximating area. And finite means you have a start and a stop. And in math, that looks like this. And sums means you're adding. Do you remember the symbol for adding a lot of things in math? Right? Capital sigma. All right. So we are going to take a couple of days to learn, or a couple of lessons to learn, approximation methods before we ever get to finding the exact area, because approximation methods are highly useful. They're very, sometimes finding the exact value of these finite sums isn't as easy, but estimating can be very, very simple. So first, we're going to make a big deal of the fact that we are transitioning between one branch of calculus to another, right? All between units 1 through 4, we really were focused on the derivative. We started with limits, then we went to approximating derivatives, then we went to the definition of derivatives, and then we went to the derivative rules, and then we went to derivative applications. Differential calculus. Now we are going to turn our attention to something called the integral calculus. And with integral calculus, believe it or not, we are going to talk about all of these things. We are going to talk about the limits and the definitions of integrals. We are going to talk about approximating. I am going to give you rules for integrating, and we are going to do applications of integrating. We will finish semester 1 at the rules. We will not get to applications of derivatives until second semester. But that is integral calculus. And a synonym for integral calculus is the antiderivative. So it's kind of like learning to multiply and then learning how to divide. It's kind of like learning how to square and then learning how to square root. It's kind of like learning how to do exponents and then you learn how to do logs. You learn how to differentiate, then you learn how to anti-differentiate. Kind of crazy, right? Math all links together. I'm telling you, it's beautiful. All right, anyway. So with derivatives, if nothing else, if you remember nothing else about derivatives, even if you forget the rules, if you associate the idea or concept of derivative with rates of change, with slope, you're in good shape. With the integral or the antiderivative, if you associate that concept with area, and I like to put area in quotes because traditional area is always positive, but your integral can be both positive or negative, but not for us for a while. For we are strictly going to be dealing with true area for the first couple of lessons. So the definite integral, definite, think start, stop, of a positive function is true area under whatever function I'm talking about, whatever height that you have, right? You have true area as long as your function lies above the x-axis. So let's talk about some methods. Believe it or not, geometry. Sometimes, even on a coordinate system, right, I have a circle. Sometimes I have a trapezoid. Sometimes I have a rectangle. Sometimes I have a triangle, right? If I have any of those shapes on the coordinate system and I recognize that, I can find the area. If I'm only talking about a semicircle, of course I take 1/2. The area of a trapezoid is 1/2 times the height of the trapezoid times the sum of the bases. Rectangle, of course, base times height. Triangle, right triangle, 1/2 base times height, right? Those are our traditional. So look for that. Look for functions that actually create trapezoids or circles or rectangles. Or what about some combo? What if you have some shape on a coordinate system that is a rectangle with some kind of semicircle on top, right? Or a trapezoid and a rectangle on top, or square on top even, right? Like, so just look for shapes or combos of shapes. First step for finding area under function, is it just a geometric shape that I know from middle school geometry? If it is not, if my bounds are not constant, like a square, linear, like a rectangle, like a triangle, or circular, like a true circle or semicircle, if my bounds are curved, we are going to approximate the area under this shape. So look at that shape I've drawn. It's not a trapezoid, it's not a circle, it's not a rectangle. It's, I don't know. So my method, one method for finding the approximate, right? If I have an actual circle, I have the exact area. If I have the exact, right, a trapezoid, that's exact area. Exact, if I have an exact geometric shape. But if I don't have an exact geometric shape, I can use something called the rectangular approximation method. Rectangular approximation method. I drew 1, 2, 3, 4, 5 rectangles underneath that curve and between the curve and the x-axis, and I don't have true area. Look, I've got too little, too much, too much, too little, too little. But it is an approximation. So how I do the rectangular approximation is I divide up the domain, start, stop, chop, 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 and then I pretend I'm constant. I go up to the function and pretend it's constant for this width of 0.8. I pretend that the function has the same height. It obviously doesn't, but I pretend it does. And then I find the area of that first triangle. Then I go up to the function and I get the height of my rectangle, and I pretend the function is constant for another interval of 0.8. And then I calculate the area of that rectangle. So this whole idea of constantizing your function over intervals. I created rectangles, and I'm just going to add them. In my case, I have 1, 2, 3, 4, 5 rectangles. Sum areas of rectangles. Which means sum a bunch of heights times widths. Right? Sum a bunch of them. How many? 1, I've got 5 of them. So I will have 1 plus 2 plus 3 plus 4 plus 5. 5 rectangles. Height times width. 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 I'm just pretending that the height is constant over chops of the domain. That is called the rectangular approximation method. It is the most famous approximation method. You don't get geometry shapes most often on your coordinate, right? Exact geometry shapes. You get irregular shapes. So the most common approximation method is the rectangular one. It's very algorithmic. It can be programmed very easily. There is the trapezoidal method, but we are not going to start with that one, right? That one is in the, but it is the same idea, the exact same idea, where you draw, instead of rectangles, you take your start and your stop. Start, stop, chop, 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 chop. You go up to the function for your 2 heights of your trapezoid and pretend your function is linear instead of pretending your function is constant over the interval. Okay, so that's a little stay tuned. That is coming. But even after you learn the trapezoidal approximation method, still the rectangular approximation method is tested more often and is used most often, but you do have to know the trapezoidal one. So let's get started. Let's example 1. To approximate the area under this curve, which I can see this curve, x squared plus 2 is always above the x-axis, so it's certainly above the x-axis on 1 to 5. Draw the function. Start, stop. Chop, chop, chop. Now, it was kind of natural for me to chop my interval like that because I was jumping by integers and it was a very nice chop. But how you chop isn't always the same. And sometimes you get to choose how you chop. So I'm going to actually erase those chops and I'm going to show you a couple of different examples of how, oh darn it, I didn't mean to erase all of it. Start, stop, right? I am going to start and stop here. Here is my function that is above the curve. I'm sorry, above the x-axis. So there is my irregular shape. I want to find the area. I'm not going to find the exact area, but I'm going to approximate it. How many rectangles did I draw? I drew 3 rectangles, didn't I? So I chopped here and I chopped here. 2 chops created 3 rectangles. They're not equal rectangles, but they don't have to be. And I don't know about you, Mr. Getz makes fun of me all the time because I love my symmetry. It kind of bothers me when they're not even, but AP loves to do this. And one of the reasons why they love it is because, as I mentioned, this is the rectangular approximation method is very easy to program, but the programs all have even intervals, right? So AP loves to put on problems that forces you into unequal intervals to make you write it out. So unequal subintervals doesn't change the fact that I can approximate this area. The area is approximately rectangle 1 plus rectangle 2 plus rectangle 3. I'm going to multiply height times width in all of these. My first height of my rectangle is f of what? F of 1, right? I put in 1, and then I pretended the function was constant over that entire interval. How long is that interval? From 1 to 2. How about my next rectangle? I pretended my height, my height of the rectangle is how high? The height of the function at 2. Pretend you are constant for an entire interval. How long is that interval? Third rectangle, what's the height of the rectangle? The height of the function when x is 3, pretend you are constant over that entire interval. How long is that one? Right? So each one of these, every time I had a function height that I was pretending was constant for a certain width, a delta x. Delta x does not have to be constant. It doesn't have to be even. Bothers me, but AP doesn't care if it bothers me. Right? So function height, constant over a certain width. Function height times a constant width, right? A constant height over a width. Function height times for a constant for a certain width. Now, hopefully you can see this estimate would be way too low, right? Can you see that? By using, right, I'm missing area here, I'm missing area here, I'm missing area here. This is a poor estimate. I mean, that's not very good estimate for the area under the curve. It's pretty freaking bad, as a matter of fact. How do you think you could make it better? Increase the number of rectangles, right? So I didn't make it all that much better, but I did make it a little better, didn't I? Now, it's not the fact that I have equal I just wanted to demonstrate having equal subintervals, right? Start and stop, same irregular shape. It's not the fact that my subintervals are equal that makes this better. It's the fact that I have more rectangles that makes my approximation better. It's still not great, but this time the area is approximately 1, 2, 3, 4 rectangles, right? And each time I'm going to use, what height am I making it constant over the first interval? F of 1, then my next height is F of 2, then my next height is F of 3, and then my next height is F of 4. True, right? Height constantize down, height constantize down, height constantize down. Who did I forget to write? Who did I forget? I didn't write the widths of each one, did I? What's my delta x? My delta x in this case is always the same, so I can kind of factor out delta x, right? See if I can not erase. I don't want to erase everything. I just want to erase. There we go. One is my delta x. Since it was constant, I didn't have to write it inside each one. I could, though. You could have written times 1, times 1, times 1, times 1. But since it was the same for every rectangle, I could just factor it out front. Notice that I still am missing area under my curve, so my approximation is still too low. But do you see, if I drew more and more rectangles, if I chopped up my start, stop, if I chopped it up, right, that would be tedious math, but I would get closer and closer and closer to the actual area. So I think you see where this is going, right? Now, this particular rectangular approximation, this time I am going to erase the pen. There are 3 types of rectangular. We just did one of them. We did something called the left hand, or just left rectangular approximation. Do you see how rectangular approximation method? The L stands for the fact that when we started, we used look at our first interval, we used the left height to constantize and go over. We used of the first rectangle, we used the left point, the left side, to constantize our height. Here's a fancy way of writing, and you do need to recognize this fancy way. Area is approximately height times width multiplied together and added up together, starting with your first rectangle and ending with how many rectangles you have. Number of rectangles, that's what that says. Same thing here, right? The area was approximately the sum of a bunch of rectangles. This is the area formula for rectangle. You've been doing that since elementary school. Height times width. Multiply them together. You got a bunch of them. You got this many of them, and add them all up, right? A fancy math way to say I'm doing area of rectangles. So on an AP calculus test, they're going to have this problem, right? They're going to have problems like this. Since you are getting points for just adding areas of rectangles, you're going to have to recognize and use the fancy notation sometimes. All right. This time, I am going to use the right hand. So instead of the left hand, notice it is the same bat channel, same bat time, but I am going to use the right hand method. I'm going to use the same add up a bunch of products. Whoops, sorry. So to do this one, Let's pretend I start at 1. Well, let's not pretend, let's actually do it. From 1 to 5. And just because I like even intervals, I'm going to do no one told me how many intervals. Sometimes they tell you. They're not going to tell you. I'm going to choose to break it up into nice, even intervals. So my width is going to be 1. My delta x is going to be 1. So I'm going to be multiplying everybody by 1. And then I'm going to get my different function heights. Right? That little subscript I just means the different ones. And then I'm going to multiply them together and add. So I'm going to make 1, 2, 3, 4 rectangles. And I am going to sum a bunch of products. Sum a bunch of products. But with the right-hand approximation method, what they want me to do is, given the first interval, which goes from 1 to 2, since I decided my delta x was 1, they want me to go to the right side. Start with the right side of the first interval, go up to the function, that's my height, constantize this way and down. So my first height came from f of 2 times 1. Go to the right side of the second interval, up to the function, make it constant, over. Up to the function, and each one of these had a delta x of 1. Notice I haven't actually bothered to give you the answers to these. An AP is actually going to often do the same. They'll just say set up, because the answer, since it's not the real area and actually it's a pretty bad approximation, they don't really often care about the number. They care about your setup. They care about your setup. They care whether you know the difference between doing left hand and right hand. They also care if you can tell what kind of approximation this is. And what I mean by that is, I shouldn't say what kind, because that kind of leads to left or right. Is your approximation too low or too high? And I hope you can see and visualize this approximation is too high. What if I had done start, stop, what if I had broken this up into only 3 rectangles and I did this one, right? What if I'd done that? I would only have 3 products that I would sum. But if I'm using the right hand rule, or the right hand method, I would go to the right side of the first interval, up to the function, constantize it, go down. Up to the function, constantize, down. Up to the function, constantize, down. So my function heights would be f of what? 2 times delta x. F of 4 times delta x, which is how big is that rectangle? How long? How wide? Right? Uneven intervals. Can you see, though, that the area of those 3 rectangles is too high? I feel like Goldilocks and the 3 Bears. Do you guys even know those nursery rhymes anymore, or whatever they're called? Goldilocks, right? Too hot, too cold, just right. All right. So this was method 2. RRAM. Method 3, of the rectangular, right? Midpoint, what do you think that looks like? Whoops, that's supposed to be an M. MRAM. Same idea, sum products, height times width. And let's again, just for the sake of, right, symmetry and beauty, let's start with even subintervals. So I'm going to chop this at 2, 3, and 4. But instead of using of the first, here's my first interval, instead of using the left side or the right side, guess what MRAM wants you to do? Use the midpoint as the height of the rectangle, and then you have to go left and right. I should have made that dotted. Go to the midpoint of the second interval, go up to the function, constantize left and right. I feel like a yoga teacher now. Go to the middle of this third interval and go left and right to be constant. Go use the midpoint of the last interval and go left and right to make your rectangles. I still have 4 rectangles, so I still have 4 products that I need to add together. This time my delta x was constant. But what values am I using? What function values am I using? I wasn't using 1, 2, 3, 4, or 5, was I? What was I using? Delta x is 1. Take delta x and divide it by 2, and I get a half. So I was using 1/2. And then add delta x, which is 1. 1/2 plus 2/2 is 3/2. 3/2 plus 2/2 is 5/2. 5/2 plus 2/2 is 7/2. Right? That's how I get these values. I find the first one by taking my delta x, dividing it by 2, and then I add delta x to get to each of these others. That's MRAM. Now it's a little harder to tell whether MRAM, what do you think? Is MRAM too high or too low? Or is it just right? Well, it's not still just right, is it? But here's what you're doing. You're trying to say, well, for each one of these, right? For each one of these rectangles, this one has a little bit of area above, and I don't know, still a little bit more. But look at this rectangle. This has a little bit of area above, but it's also got below. Right? And you kind of have to think of, well, those, you have to kind of have a really nice drawing to say like, what do I think? Too high or too low? It's not as obvious, is it? So you might actually have to compute values, or, maybe we start thinking about some, right, trying to be a little bit more precise. Maybe the shape, what is the actual function doing? All right. Here is a picture of LRAM 4. Look at this 4 down here. The subscript tells you how many rectangles you're using on the subinterval, right? The left-hand approximation method with 4 rectangles. There's RRAM sub 4. That means I used of the first interval, I used the right side of it to constantize my function. For LRAM, I use the left side of the first interval to constantize the function. MRAM, oops, that's supposed to be a subscript, means you used the middle of the function to constantize right and left to get the first interval. Traditionally, so this is not for sure, traditionally this notation is used when your subintervals are even, but not always, but it is tradition. And again, somebody will say to you, AP will tell you how many rectangles they want over what interval they want. Okay. And they might say, use the left-hand rectangular approximation method with 7 rectangles. So I would have to take this distance from 0 to 4 and divide it by 7, right? If I wanted 7 equal. Now, notice that with each one of these examples, my function was increasing. When my function was increasing, LRAM was too low. When my function was increasing, LRAM was too high. When my function was increasing, MRAM, supposed to be subscript, was probably the closest, but I'm still not sure. Is it too high or too low? But I can do calculations to find that out. And again, we will talk a little bit more about MRAM later. But I don't want you to you don't always have increasing functions now, do you? Look at these decreasing functions. What if I did LRAM RRAM and MRAM with decreasing functions? Can you draw it while I'm writing this out? What do you think happens? LRAM, let's say I divide this into 3 rectangles, each one into just 3 rectangles. Start, constantize, and down. Start at the left of each interval. Up, constantize, down. Up, constantize, down. With a decreasing function, LRAM is too what? Too high. But what about RRAM? Start here. Here's my first interval. Go to the right side, constantize and over. Right side, constantize and over. Right side, constantize and over. RRAM on a decreasing function is too low. How about MRAM? Here's my start. Go to the midpoint and constantize left and right. Constantize left and right. Constantize left and right. Still not altogether sure how I tell with MRAM. All right, let's put some units on here. I hope you're sitting down because your mind is about to be blown. Find the velocity in meters per second of a particle where its velocity is given by this parabola. Use LRAM with 4 rectangles to approximate, I thought we were approximating area under a curve. First 4 seconds. Oh, that's start and stop. What's going on here? What the heck? Well, there's my parabola, right? 1/8 t squared plus 1 starts at 1. It's relatively wide. But what are the units on your y-axis? Your units on your y-axis are meters per second. What are your units on your x-axis? Seconds. They wanted me to use LRAM over start at 0 and stop at 4. That is an irregular shape. It is not a normal geometric shape like a circle or a trapezoid or a rectangle. So I'm going to approximate. They asked me to use LRAM with 4 rectangles, with the first 4 seconds going from 0 to 4. Let's see if I'm 0 to 4, and I want 4 rectangles. Well, how wide is that? 4 minus 0 is how wide it is. And how many rectangles did I want? So each one has to be a width of what? 1. So I'm going to do my first interval, and I'm going to go to the left side, constantize, and over. I can see that LRAM with an increasing function, my approximation is going to be too low. There's my values, and I just write, so I'm right, just all I'm doing is plugging it in, right? I plugged in, right, V of 0, V of 1, V of 2, and V of 3. Again, don't really care about those values because this approximation is terrible. This time I just typed it out and I gave you the approximation. But look at this unit on the end. What is happening? Remember, this is height times width of a rectangle. Height times width of the rectangle. But what are the units of your heights? The units of your height are meters per second times, what are the units on your t-axis or your x-axis? Seconds. What happens when you multiply meters over seconds times seconds? By, and you get meters. What the heck? The area under this freaking curve, because of these units and because you multiply, you get meters, you freaking get distance out of this. Those of you that are in physics are not surprised by this. What? Freaking area of rectangles approximates distance. What the freak? Mind blown. I'm really sad that I'm not in person with you so you can see the shock on my face. You can see my hands. You can see me, like my hair just like standing on end. What is going on? What's going on is that math is beautiful and you can't do any physics without math. Math is queen. You hear that, Mr. Getz?
I'm ignoring you.
Oh, did you hear that? He's ignoring me. That's not a good husband thing to do. And again, because my function is increasing, LRAM gives me an underestimate, right? That's why. What if I asked RRAM? What if I asked you to do RRAM? Right? Now I'm going to go through this very fast because it's the same phenomenon, right? There's my rectangles. There's my values. But notice that this time I am using V of 1. I rarely write out the 9/8, the 3. I only write these out if I need to because honestly a program is coming up with that number for me. I write V of 1 times 1, V of 2 times 1, V of 3, V of 4. And I usually factor out delta t or delta x when it is constant. And yes, even though it's multiplied times 1, I write 1 so that my grader understands I know what my delta t is. Now, I want you to notice the difference between in the right-hand approximation method, there are actually 4 function values in play. 0, 1, 2, and 0, 1, 2, 3, and 4. Who did not get to come to the RRAM party? Right? V of 0 didn't get to come to the RRAM party. Sorry, you're left out. Get it? Left out. But look at the LRAM situation. In LRAM, there are still 5 function values in play here. Who got left out of the LRAM party? the last one, right? Because this is V of 0, V of 1, V of 2, and V of 3. So when you're doing an approximation, an LRAM or an RRAM, remember somebody's always going to be left out. Either the first or the last function value doesn't get to come to the RAM party. It's a little exclusive. Now remember, the first one was too low. It was, I don't know, I forget already. 5.75 was LRAM. 5.75 was LRAM. 7.75 was RRAM, and that was too high because I had an increasing function. Here's MRAM. And again, I'm just going to show you what this, right? Look, had this drawn automatically. I certainly am not calculating all of those out. Again, I'm letting my calculator do that. Look at my MRAM. In between 5. Remember, LRAM was 5.75 meters. RRAM was 7.75 meters. MRAM is in between. And this, but this number, AP doesn't want this. What AP wants is this. They want to see four products that you add together. You do not have to write these values out. Write V of the midpoint. Okay. Notice that when we were rounding, though, we did put 3 places past the decimal. 5.75 was exact, 7.75 was exact, 6.625 was not. Now, I'm going to tell you that MRAM is an underestimate. It is an under. Right? And maybe with this I've drawn, instead of just me hand drawing, can you tell? Can you tell here that each of the areas that you're missing is slightly bigger than the too much area? And here's another hint to how you can tell. What if you did like the secant line between each one of these? Can you kind of tell like the average there? Right, it's a little bit easier to tell which rectangle is bigger, which rectangle is smaller, right? All right, so again, in this example, because our units were meters per seconds versus seconds, and the integral is just area of height times width, which means you're multiplying meters per second times seconds, you actually got the distance over the first 4 seconds. That is kind of crazy. And all I'm doing here is showing you how can I get a better approximate to the actual distance? It's by making more rectangles. I know that MRAM usually gets closer than either L or RRAM, so I did MRAM. And again, I'm not doing this by hand. I'm doing this with, right, a computer. Now, do notice how I got this number, though. What do you think that number is? It's still the first 4 seconds. So, how wide is the entire interval? How many rectangles do I want? So 1/2 is my delta x, but I want to use the midpoint formula. So if this is a distance of 1/2, to use MRAM, I want to take delta x and divide it by 2, which is the same as multiplying it by 1/2, which is 1/4. and then I'm going to add a half each time, right? I'm going to start at a fourth or 2/4. So V of 1/4, and then add 2/4. Add 2/4, right? And that's how I'm going to travel through my interval from 0 to 4. There was my sum. So I'm getting better, right? I'm getting better. I'm still an underestimate, right? Because of the increasing and shape of this graph as I'm rising. That's the sum of all of my, right? Sum of all of the heights. And then since my delta x was constant, I factored it out front, or delta t was a half. It's an underestimate, still pretty good. The actual area exactly is 6 2/3 meters. So 6.65 is pretty close, right? With just freaking 8 rectangles, I got pretty close. That's amazing. And the math is programmable, easily programmable, and not challenging. It's areas of rectangles. So how do we obtain the exact value? Well, that's calculus, right? Exact takes calculus, and I think you can kind of see, right, where we're going. More and more rectangles, right? More and more rectangles, more and more chops of the interval. What's the L word that goes with that? Forever. Limit. The exact area of a function that's positive, that lies above the x-axis, is the limit as the number of rectangles goes to infinity, but it is just adding a bunch of products of heights times widths. It's just your width is getting infinitely small, and you can't do that, a matter of fact, approaching 0, and you can't multiply by 0 and get area unless you use calculus. So this is an idea. Now notice this function is both increasing and decreasing, concave up and concave down. You make more and more and more rectangles, you will get closer and closer to the exact area. It doesn't matter whether you're doing the left, right, or midpoint. If you have infinite rectangles, it doesn't matter. You will get the exact area. Kind of cool. So here's a QR code that will take you to this, or here's a link to a Desmos application that'll let you play around with this function and let you increase and decrease the number of rectangles. Oh my gosh, how bad of an estimate is that, right? 2 rectangles. And it'll let you play around with your delta x, right, and using your function heights or whatever, and is a very nice visual. So please feel free to play around with this and use any. Desmos also has, right, and GeoGebra, places where you can just Google, how do I do, right, RAM calculators. You don't want, and RAM programs. If we were in person, I would have given you one for your calculator. I would have linked one to you, but you can very easily, again, find these on the internet. And AP is going to test you not on the final answer. They're going to test you on the setup. So it doesn't really matter if you have a program on your calculator when you're taking the test to do this or not. So how will you be tested by AP and by us? You are going to be asked to approximate, even after you know how to find the exact. You're going to be asked to approximate the area with LRAM, RRAM, or MRAM. And N, remember, is how many rectangles they want. They could also ask you to do the trapezoidal rule. We just haven't learned that one yet. Notice exact area is with a limit, but approximate area, I don't know why I only had approximate area, does not have a limit. That's where the N comes in. 5 rectangles, 10 rectangles, 50 rectangles. AP will give you, is much more likely to give you uneven intervals. They might give you even. Your book does a lot of even, I think, but AP loves the uneven intervals. Most of the rubric points will be in the setup, not the answer. So how are you getting the heights? Your function values, right? F of what? And are you leaving out the left endpoint? Are you leaving out the right endpoint? Are you just using midpoints? So do you have the right function heights? Do you have the right widths? Again, is your width even or not? And are you multiplying all of those heights and widths together and then adding? And remember, if delta x is uniform, if it is the same, you can factor it out. You don't have to, though. All right. Multiplying and adding, and then sometimes they will ask you if your estimate is too high or too low, and they do that with, I was purposely ambiguous with the MRAM. AP is mostly gonna ask you only about LRAM and RRAM. Is it obviously too high or obviously too low? And they're gonna ask you to justify, and you justify it with the function is increasing or decreasing. All right? So please, again, think about when you're doing your book homework, sometimes you are asked for 50 rectangles. I don't expect you to do that by hand. Find yourself a nice, and share with each other, right? Oh, I found this one, I found that one, right? On the internet. Riemann calculators. I don't think I've used this language with you yet, so I want to tell you. Riemann. Riemann sums. Riemann sums. Georges Riemann is a mathematician that came up with this idea. And Riemann sums just means sums of products, which is why the integral is an infinite Riemann sum, because you are summing a bunch of products. Okay. So Google that. Google Riemann sum calculator. Tell me what you find. Have a great day, and I will see you in our next live session.